Hello again. We're going to finish off Chapter 4 today in Section 4.5 with what we call an introduction to functions. The concept of a function is something that we will build upon during the course of the semester. So that's why this is just an introduction to it. Each time we introduce some new types of functions, we will review what we already have learned, okay? Because it's something that doesn't quite go away, so we want to make sure that it stays fresh. But before we actually define what a function is, we have to initially define what is meant by a relation, okay? Now, a relation, from a mathematical perspective, is simply a set of ordered pairs. Now, we have been working with ordered pairs throughout Chapter 4 when we were graphing. Okay, we plotted those coordinates, those points. Your set of ordered pairs, once again, is made up of an x and a y. Okay, and what do we mean by a set? Is that there just has to be more than one ordered pair. For example, example A, let's say, might be made up of the ordered pairs -2, 3, 0, 5, 1, 6, 3, 8. And what we have here is a set of ordered pairs, and therefore we would say this is an example of a relation. Let's take a look at another example. Let's say we have the ordered pairs -1, 1, 0, 0, 2, 4, and 3, 9. Here we have another example of a relation because it is a set of ordered pairs. There's a distinct mathematical relationship from part A, and there's also a distinct mathematical relationship that creates set B, example B. Let's take a look at a third example, example C. Let's say we have 4, -2, 0, 0, 1, 1, and 4, 2. Here we have another set of ordered pairs. Therefore, by its definition, we would say that this is a relation. And let's just do one more example. Let's say we have -3, 3, 0, 0, 2, 2, and 3, 3. This is a fourth example of what we would consider a mathematical relation because it is a set of ordered pairs. It is multiple ordered pairs. And once again, there's a relationship between the x's that would form these y's. Okay? So now that we know what a relation is, next we want to define what is meant in math by a function. Now, by its definition, a function is a special relation where x doesn't repeat. Okay? So a function has to be a special relation. It has to be a special set of ordered pairs where the x value doesn't repeat. So let's go back to our 4 examples here. And of our 4 examples, we want to know which of these relations are special to consider them whether or not they are in fact functions. So if I look at example A, I want to look at my x values and I want to make sure that x doesn't repeat. So here I have an x value of -2, 0, 1, and 3. In each of these cases, your x value never repeats. Therefore, not only is this a relation, but it is also a function, because it is special enough because our x values never repeat. Let's take a look at example B, and we'll look at the x values. -1, 0, 2, and 3. All of the x values are different. Never does the x value repeat. Therefore, once again, it is, in fact, special enough to be considered a function. Let's take a look at example C, this relation. Is this relation special in that the x value never repeats? Well, let's take a look. Here we have an x value of 4, 0, 1, but then we have the x value of 4 again. Okay, so that x value of 4 is repeating. So that's why we can say that example C is not a function. It is still a relation because by its definition, it is still a set of ordered pairs. But it is not special because that x value of 4 repeats, and that breaks the rule. Let's take a look at example D. In example D, we have our x values of -3, 0, 2, and 3. The x values are all different. None of the x values are repeating, so therefore it is considered special and therefore would be considered a function. Don't worry about in example D the fact that the y value repeats. Okay, here you have a y value of 3 and the same y value of 3. That's okay. Y can repeat. It's the x value that cannot repeat. Now, when we have a function and we talk about the ordered pairs, the coordinates of x and y, sometimes we use some different special names. After all, a function is special, so we would want to refer to our x and y values with special names. Sometimes your x value is referred to as the input. The y value is often referred to then as the output. Your input and output make up your x and your y values of your function. Okay? Two other very popular names that we will see a lot here, as well as in other math classes. Your x value, many times in terms of a function, is called the domain of the function, what x could be. The y value, or the output of a function, also has a very special name, and it is often referred to as the range of a function. And you will see these words a lot, domain and range, throughout the textbook for this course, as well as for many other higher math courses, like whether it be calculus, pre-calculus. Those math courses tend to use this terminology of domain and range when you are talking about the x and y values of a function. So you do want to be familiar with the terminology, okay? Now, how do we write a function? What's the special function notation that we use? Okay, well, function notation looks something like this. F of x is going to equal, let's say, 3x plus 5. F of x is your notation that represents we are talking about a function. And you'll notice what's inside the parenthesis, the variable x, can also be found on the opposite side of the equation, okay? Because what's inside your parenthesis, your x value, is your input. What you get out, your f of x, is considered the output, okay? What's inside the parenthesis, that variable, represents the input. F of x, okay, that entire thing is your output, okay? And we have this rule here of 3x plus 5. That's kind of like the formula that you're going to follow. That's your algebraic expression that represents this particular function, f of x. If I change the algebraic expression, let's say instead of 3x plus 5, I might have 1/2 x minus 2. By changing the algebraic expression, it is customary that we change the very first letter in front. So I wouldn't use, let's say, f of x anymore. I might use g of x. This variable x has to be the same as this variable x here, okay? Because this is your input, and that's what you have to plug in to your function. What changes is the letter in front of the parenthesis. Let's say I change it once again, a different algebraic expression. I might have, let's say, x squared plus 2x minus 3. Here we have a different function, okay? Once again, that was an x squared plus 2x minus 3. By changing the algebraic expression, the rule of the function, I would once again have to change the very first letter, in which case I might use, let's say, h of x. If I was to change my rule one more time, let's say we had 3 over x, okay? I would have to change the very first letter, so I might use, let's say, j of x. Each time you have a different rule of your function, you change the first letter of your function notation, okay? Now, we are going to learn all different types of functions. This first one here, f of x, equals 3x plus 5. Now, you have seen something like this already, all right? You have seen a linear equation in the previous 2 sections where we talked about y equals mx plus b. This was an example of what we called a linear equation, remember, in slope-intercept form. Well, this is the same idea. F of x equals 3x plus 5. That is what we would consider a linear function. Okay? Why is it linear? Because it's x to the first power. Okay? G of x, okay, 1/2 x minus 2. That too is a linear function. It's of the same form, y equals mx plus b, that's slope-intercept form. H of x, okay, we're going to see things like h of x later on throughout the semester. H of x is known as a quadratic function. And the reason why it's considered a quadratic function is because the variable x is being squared. And whenever you have an x squared as your highest power, that's when we have what we consider a quadratic function. J of x also is something a little bit different, okay? 3 divided by x. When you have a variable expression in the denominator, this is now considered a rational function. So there are all different types of functions that we are going to learn about, okay? And we're going to see how to graph some of these as well, okay? Not right now, though. As like I said, this is just an intro to functions. Later on, when we learn about quadratics and radical functions and logarithmic functions, those are all different types of functions that we will be learning about here in intermediate algebra. Maybe next semester when you take pre-calculus, you will learn about the sine, cosine, and tangent functions. Those are the trigonometric functions. Okay, but that's something that you will learn more about in pre-calculus maybe next semester. Now, that is the notation. Okay, we have the algebraic rule on the right side, and we have this f of x, g of x, h of x, j of x. That is your function notation, okay? Now, one thing that we often do with functions is we evaluate functions. Okay, we want to evaluate a function. For example, let's say we are given, maybe we are given f of x equals, let's say we have 4x minus 5. That is the rule, okay? 4x minus 5, that relationship is equal to our function f of x. I could ask you to, let's say, evaluate f of a, let's say, negative 3. I could ask you to evaluate f of 0. I could ask you to evaluate f of 2. I could ask you to evaluate f of, let's say, 1/4. And when I ask you to evaluate a function, I have to not only give you the rule, but as you'll notice here, I have to give you a number that you're going to substitute in for your input for your x value. Okay, I have to give you the domain. In which case now, I am going to replace the x into my formula. So instead of 4 times x minus 5 for the first one, I would have to do 4 times negative 3 minus 5. I replaced the x with the value that's inside the parenthesis. Whatever's inside the parenthesis, I have to replace the variable. And then we would simplify using, of course, the order of operations. Well, 4 times the negative 3, that would be negative 12 minus 5, in which case we would get an answer of negative 17. If I want, I can express my answer as the ordered pair, that when I plug in a negative 3, we get out a negative 17. Negative 3 is the input. Negative 3 is the domain. The negative 17 would be the output or the range. Okay, I'm going to try to use that terminology as much as possible. Now let's say same function f of x equals the 4x minus 5. I want you to evaluate f of 0. So I'm going to input 0 wherever I see the x. So that would be 4 times 0 minus 5. When we simplify, 4 times 0 would be 0 minus 5, and we would get a solution of negative 5. So our ordered pair, 0 is the domain, negative 5 is the range. Let's plug in the number 2. Let's say we had 4 times now 2 minus 5. Of course, that would be 8 minus 5, which of course has a numerical value of 3. So our ordered pair would be, plugging in 2, we get out a 3. We plugged in a negative number, we plugged in 0, we plugged in a positive number. Can I plug in a fraction? Sure. I would have to write this as 4 times 1/4 minus 5. When we simplify, 4 times 1/4 would be 1 minus 5. And when we perform the order of operations of 1 minus 5, we get a negative 4. So our ordered pair would be 1/4, negative 4. So when I ask you to evaluate a function, not only do I have to give you the rule, okay, the formula, the recipe that we have to follow, but I have to give you an x value to plug in. Now, in all of these cases, x was a number, and that's perfectly fine. X doesn't always have to be a number. For example, same function, f of x equals 4x minus 5. I could ask you to, let's say, evaluate f of maybe a plus 2. Now, don't be alarmed here. Just like I plugged in the numerical values of -3, 0, 2, and 1/4, I plugged those numbers in for x. I have to do the same thing now for this algebraic expression. So instead of 4 times the x, or the 4 times the input minus 5, I would now have 4 times a plus 2 minus 5. Now we just want to simplify this. To simplify, I would want to start by distributing my 4. 4a plus 8 minus 5. Further simplifying what we can here, we would have a 4a plus 3. That's the output, okay? And just like we wrote these answers as an ordered pair made up of the input and the output, I could say that the answer would be a plus 2, that's the input, and 4a plus 3 would be the output. Okay? So, if we plug in a number, we get out a number. If I plug in an algebraic expression, I'm going to get out an algebraic expression. Okay? What if I changed my function? Let's say we were given g of x equals x squared minus 3. I could ask you to evaluate maybe g of -4. I could ask you to evaluate g of 0. I could ask you to evaluate g of, let's say, 5. And just like before, wherever I see my x value, that's the input, I have to substitute it into my rule. So, for the first one, when I evaluate g at -4, I have to take the -4 and square it, and then I'm going to subtract 3. Well, -4 squared would be 16 minus 3, or simply 13. So our solution would be -4, 13. Let's try plugging in now g of 0. Okay, so I would have 0 squared minus 3, in which case we would have 0 minus 3, which is a -3. So our ordered pair would read 0, -3. For the last one, same function g of x, or x squared minus 3, but now we have to plug in the value of 5. So now I would have 5 squared minus 3. Simplifying, that would give us 25 minus 3, which we know to be a 22. So our ordered pair would read 5, 22. Okay? Let's do one more. Let's say we are given h of x equals, let's say, x plus 1 over x minus 2. And I want you to, let's say, evaluate maybe h of -1. I could ask you to, let's say, evaluate h of 0. And I might ask you to evaluate, let's say, h of 3. We want to be careful here. Wherever I see the variable x, I have to plug in the number. So when I look at my rule, I have two x values. So I'm going to have to plug in those numbers into both x values. So the first one would become -1 plus 1 over -1 minus 2. When we simplify, we would get 0 over a -3, which is 0. So our ordered pair would read -1, 0. Let's take a look now when we plug in 0. We substitute in 0 wherever we see an x value, in which case we would have now 0 plus 1 over 0 minus 2. When we simplify, I would have a 1 on top and a -2 on the bottom. And so now this ordered pair would be 0, -1/2. Let's do the last one now. We're going to evaluate h of 3 for our function h of x. And if I do that correctly, 3 plus 1 goes on the top, and then we're going to have 3 minus 2 on the bottom. When we simplify what we can, we would have a 4 on top, 1 on the bottom, which is of course simply the number 4. So our ordered pair would read 3, 4. Okay? So that's how we evaluate a function, and that's one thing that we will always try to do with a function. What do I need to give you? I need to not only give you the rule, but I also have to give you an x value to plug in. Whether you plug in a number or an algebraic expression, doesn't make a difference. When we plug in a number, you get out a number. When you plug in an algebraic expression, as we saw here with the f of x function, we got out an algebraic expression. Now, the other major concept that we address here in this intro to functions is I could ask you to identify the domain of a function. Now, we talked about what's meant by the domain. The domain are the x values. It's the input. And if I'm asking you to identify the domain, I want you to tell me what are the possible x values that work for the function. Now, for example, we had the problem when we talked about f of x before. F of x was 4x minus 5. So let's take a look at that function once again. 4x minus 5. Okay, that's the one I gave you when I asked you to evaluate the function. And when we evaluated it, let's take a look at what kind of numbers we used. We evaluated it at -3. We evaluated at 0. We evaluated at 2. We were even able to evaluate it at 1/4. Okay? Now, and that is because when it comes to the domain of your linear function, there are no restrictions. Okay? What we can say here, x is all real numbers. The domain, there are no restrictions. X could be anything at all. No matter what I plug in for x, I can multiply it by 4 and subtract 5. Recall we use certain interval notations for that. The interval notation for all real numbers would be from -infinity to infinity. Okay? There are no restrictions on the domain of this linear function. Okay, and that's going to be true for all linear functions, actually. If I said g of x equals maybe a -5/3 x plus 2, here we have another linear function. And if I was to ask you for the domain of this particular linear function, you're simply going to tell me negative infinity to infinity, all real numbers. Because no matter what number I substitute in for x, I can always multiply it by a negative 5/3, and you will always get something that is mathematically defined. Okay? And like I said, that's going to be true for all linear functions. Even if I had maybe a quadratic function. Let's talk about the quadratic function for a moment. For example, maybe h of x might be equal to, let's say, x squared plus 5x minus 8. Here we have a quadratic function because of this x being squared. And no matter what I plug in for x, any number can be squared. Any number can be multiplied by 5. Never will it be an undefined mathematical expression. And that's why, as far as the domain is concerned, we would be able to say that the domain is all real numbers, from a negative infinity to infinity. Now, what type of function might there be a restriction, a value of x that can't happen? Well, that happens when we talk about the rational functions. For example, let's say f of x might equal 8 over x. I could ask you to evaluate many different values. I could plug in many different values for x. I can plug in, let's say, a negative 4, because 8 divided by negative 4 would give you a negative 2. I can plug in, let's say, a positive 2. 8 divided by 2 would be 4. That makes sense mathematically speaking. I could plug in a fraction. Let's say I want to plug in 1/3 in for x. 8 divided by 1/3 would give you the number 24. Okay? Everything is mathematically defined there. Okay? But there is one number that x could never be. There is one number that I could never ask you to evaluate x at. And if you were to think about your denominator, particularly when we were doing graphing, we talked about if you have a particular number in your denominator that it would cause the fraction to be undefined. And in this particular case, that would occur when x equals, or should I say in this particular case, x can't equal 0. That would be the domain. That would be your restriction on the domain. That would be the one value of x that can't happen, because 8 divided by 0 is undefined. So it is a 0 in your denominator that would cause your restriction on your domain. Let's try a different rational function. Let's say g of x might equal 8 over x minus 4. Now, once again, there is one value of x that I cannot substitute in to this particular function. There's lots of values of x's that I can plug in. I can plug in, let's say, a negative 4 for x. I can plug in a 0 for x. I can plug in a 5 for x. But the one number that can't work, okay, well, what's going to concern us once again is the denominator. That denominator of x minus 4 can never equal 0. And so, if we were to add the 4 over to isolate the x, we would be able to say that x could be anything except the number 4. Okay? 4 is the restriction on the domain. Why? Because if I plugged in 4 into my rational function, this particular one, I would get a 0 in the denominator, and we don't want that. Let's try another. Let's say h of x that might equal, let's say, x minus 5 over x plus 3. Here, once again, we have one restriction on this particular function. Don't concern yourself with the numerator x minus 5. That's not the problem. Once again, it's the denominator of x plus 3. X plus 3 can't equal 0. And so now, by subtracting the 3 over, we would get our restriction in that x could be anything except a negative 3. Because negative 3 would cause this denominator to be 0, and we don't want that. Let's just try one more. Let's say j of x is going to equal maybe x squared plus 1 over 2x minus 3. Now, once again, we don't concern ourselves with the numerator x squared plus 1. What worries us, what causes restrictions on the denominator, once again, is if 2x minus 3, that can't equal 0. Always set the denominator not equal to 0. And now we have to solve. I would add the 3 over, in which case 2x can't equal 3. And if we divide both sides by 2, we would come up with x can't equal 3/2. That would be your restriction on the domain. Okay? So you can either tell me what x is, as we demonstrated with these linear and quadratic functions. Here you're telling me that x is all real numbers, that there are no restrictions. Or as we see with these rational functions, when you have a rational function, you do have certain restrictions on what x can be. All right, so you have to be careful of that. All right, that completes today's lesson, as well as completes Chapter 4. Give the homework a try that goes along with this material, and please feel free to email me any questions as you have been doing so far. All right? Until the next time, be well.